All right, lecture 5, let's get started. Welcome back to Engineering 213. How did the last homework go? I imagine that one was a little bit on the trickier side compared to the previous two. Some of that was kind of on purpose. The idea behind this assignment is maybe sort of to flex the trig muscles a little bit and to get back into these types of computations, but also maybe to say that right now the way that we're describing vectors is a bit messy, that there's probably a better way of doing it. And spoiler alert, there is. We're going to do that using IJ notation, or IJK notation, if we're talking about 3D. And I'll talk a little bit about that today. Before we get to IJ or IJK notation, we're going to handle another type of problem, though, related to what we've been doing so far, which is sort of how to compute unknowns related to vectors, because really the two types of problems that we do in this class, at least when it comes to forces and moments, are, for one, summing them up, and two, figuring out what the unknown needs to be in order to generate some result. And so that's going to be kind of our goal for our example today. In terms of the housekeeping, so everything up to the homework that you submitted today is graded. Did anybody have any technological issues with uploading this one? Everybody good with that? Okay, good. You've got a homework that's assigned today that's due Friday. I'll go ahead and tell you I am going to give a homework Friday, but it's not going to be due Monday. It's going to be due Wednesday. And it's not going to be any longer. I'm not saying, ooh, I've got more time to give you a bigger assignment. I'm not doing that. In fact, the homework that you get on Friday, I imagine you'll breeze through. In an odd way, I'm going to give you more vectors to deal with, but you'll do it faster. Trust me, it's a lot more straightforward. All right, so far so good? So one of the things, I know I'm sort of, I guess, contradicting myself a bit, but I did want to say a few things about the last homework that you did, because I want to sort of illustrate a failing of the way that we've been describing vectors so far. Now, it is true that vectors have a magnitude and a direction, and as long as we describe those, I guess, in an unambiguous fashion, then the description is correct. But even that could have multiple different ways of description. So, like, for example, let's consider the following vector. Okay, so let's assume that I have a coordinate system, something about like this. Let's assume that we have a magnitude of, 200 pounds. And let's assume that we have been given an angle of 70 degrees. Now, I'm really just making this up, okay? So I have 200 pounds at some angle down from the horizontal of 70 degrees. Okay, and we'll call this vector, consider the following vector A. So I think everybody would agree, at least from a graphical perspective, this is an unambiguous description of the vector, right? We have a known point of origin, we have a magnitude, and we have a direction. That's pretty clearly identifiable. In other words, nobody in here is going to look at this diagram and come up with a different interpretation of what's going on, right? We're all kind of say the same thing. But how would I describe that with just numbers? And that's where things kind of get a little messy. So one way of describing it would be 200 newtons, like that. That's a way of describing it, right? How about this? Could I do that? That would work, right? How about this? I mean, would that work? See what I mean? These all mean the same thing. And that is sort of a problem with the notation that we're using right now, is that, yeah, it works, but I could come up with at least 3 different ways of describing this vector, and they're all right. They're all correct. So, I mean, I guess maybe the big point is I'm going to have fun grading this homework 2.1 because I'm going to get different answers from everybody that could all be correct, right? But that's on me, right? So I would argue that we need to develop a consistent means by which we can describe vectors so that we're all saying the same thing. And IJ notation for 2D or IJK notation for 3D will resolve that. There are some other added advantages of describing vectors with IJK notation, and one of the big ones is that vectors described that way can be multiplied easily. We have 2 different ways of multiplying vectors. We can either multiply vectors to generate another vector as the product or a scalar as the product. You might have heard the terms dot product and cross product before. Has anybody heard those? So describing vectors in that fashion affords us the opportunity to develop a methodical way of doing that. But we'll get to that here in a bit. If you haven't heard of IJK notation, we will get there. I am going to use this notation one more time for today's lecture, largely because of the way that we formulated the problems for today and the problems for the homework. I think the ambiguousness of the problems is going to sort of go away because you'll see the way the problem's formulated. It's going to be much more clear what we're after. So that part won't be a problem. What I want to go through today is the idea of figuring out an unknown for a given problem. In other words, our last lecture was focused on here's vector A, here's vector B, add them. Okay? Now what I'm going to do is I'm going to give you vector A, but I'm not going to give you vector B. And I'm going to say, okay, I want to know what vector B needs to be in order to obtain a given result. Okay? And that's going to be our focus for today's lecture. So just to recap from Monday, make sure we're all on the same page. I have already talked about this, but just to make sure, we are talking about vectors, and a vector is a mathematical object that contains 2 facets, a magnitude and a direction, okay? Whereas a scalar contains only a magnitude, okay? Now, vectors can be multiplied by a scalar to change their magnitude. So if you take a vector and you double it, it will stay along the same line of action. It will just double its length or its magnitude. If you multiply a vector by a negative scalar, it will stay along the same line of action. It just flips the direction. Okay. Now, when we add vectors in this tip-to-tail graphical fashion. So if we have 2 vectors that are applied at the same point, P and Q, and we want to determine what is the sum of P and Q, what we'll do is we'll take P, place it here, take Q, move it onto the tip of P, and figure out how far it is from the beginning to the very, very end. Okay? And so because of that graphical nature of vector addition is commutative. Okay? In other words, P plus Q is the same thing as Q plus P. And by the way, something I did sort of sidestep, and I guess I don't know where everybody's at in your calculus sequence. If I throw this symbol, does everybody know what that means? Big Greek letter sigma, that references a sum. Okay, so if you ever see the big Greek letter sigma, that just means the sum. So what I am saying is that the resultant of a group of vectors is the sum of those vectors. Okay, that's what I am saying with that notation. Okay? All right. So far, so good? Okay. So my main star of the show today is actually this example. Okay? And so first off, to be clear, in the example, what I'm ultimately going to be after is the magnitude of this tensile force and this angle. So we're not going to have to come up with a way of expressing that because we'll be able to do that, I think, pretty easily. I don't think that'll be a problem with our example today. But let's go through the description of the example so we kind of understand what's going on. So I have here a vehicle. Let's say the vehicle is stalled or it's broken down, and I'm trying to pull the vehicle across the street. Okay. Now, one person is pulling the vehicle with a rope that's kind of like this. Another person is pulling the vehicle with a rope that's going something like this. Okay. Now, we'll call this person B. Okay, is pulling the vehicle with a tensile force of 3 kilonewtons. Okay, and they're yanking the vehicle at an angle of 30 degrees from the horizontal. Okay. Now, person B needs to supply some amount of force at some angle. But the question is, what is that force and what is that angle? Well, that's related to the goal. So what I want at the end of the day, at the end, when both of these forces are applied, I want the resultant of these forces to be a horizontally applied load of 4.8 kilonewtons. Okay? So the question is, what is the magnitude and direction of that second force? What is the tension in rope AC, and what is this angle? Okay, so that's going to be what I try and determine in this example. So ultimately, I'm trying to come up with this. Okay, everybody kind of understand the problem? Like maybe not we're going to go through how to do it, but everybody kind of get the idea. Okay, all right. So come on. Didn't want to end there for a second. Okay. Okay. So here's our problem. Okay, and let's see. Let's do some vector descriptions. Okay. All right. So let's describe some vectors. Okay. So the first thing I'm going to do is I'm going to describe vector AB. And I'm going to call it, this is the notation that I'm going to use. So I'm going to use the tension in rope AB, so T sub AB. And the way I'm going to describe that is I'm going to say that it is 3 kilonewtons. Sorry about that. I'm going to try and keep that to a minimum. At an angle of 30 degrees. Bless you. Okay? Now, I do know what my resultant needs to be at the end of the day. Okay? And again, notice anytime I describe a vector, I am using the little arrow over the top of the vector. Okay? Now, I'm going to say that the resultant needs to be 4.8 kilonewtons, but what does the angle need to be if I were to describe it like that? 0. Okay? And as for T sub AC, now this is my unknown. What I'm going to do for T sub AC is I'm going to say it's some magnitude but what I'm going to do is describe it. See if I can do better than that. Like that. So if I can figure out the magnitude and I can figure out alpha, I have this vector described. Okay. So far, so good? So now let's see if we can come up with a graphical representation. And before we do that, I think what I should do is make sure that we are clear from this that the resultant is that plus that. Okay? In other words, I am going to start with vector AB, then draw vector AC, and the end result from beginning to end should be my resultant vector. So let's see if I can represent that graphically. All right, so let's see. Sorry, I'm trying not to scooch up and down too much. So let's start out here. I'll put a little coordinate system down here for the very beginning. And let's start off with vector AB. So vector AB, I'm going to draw it something like that. So we'll say that the magnitude is 3 kilonewtons, okay? And we'll say that this subtended angle is 30 degrees. Okay? Everybody okay with that? Now, what does the resultant look like? The resultant is a flat vector like that, right? So the resultant, let's draw that like this. And I'm trying to draw it to scale. So this is a 4.8 kilonewton vector, so it's going to be a little bit longer. Okay? So far, so good? Now, so what we need to figure out is that vector. This is the vector we need to figure out. We need to describe that one. Okay? And we need to figure out that as well as its direction. Okay. Now, I am curious. All right, so first off, let's be clear. Let's look at this problem. This is a triangle. I have this leg figured out, and this angle. So I have enough information to solve for everything else in the triangle, right? We could do that now, and that would be a fairly straightforward mathematical exercise. But I want to make sure that I am describing things accurately, okay? And really what I'm after is I just want to answer the problem, okay? So let me draw a little coordinate system right here, okay? So remember, I'm after this angle right here, that angle. So that's this, isn't it? That's this. So I'm after here. I'm gonna move this down. I don't want this to squinch up a little bit. I'm gonna move that down. So I'm after this angle, which is alpha. Can anybody tell me how alpha relates to this triangle? If this is alpha, does alpha figure out anywhere inside this triangle? Where is alpha in this triangle?
In the bottom right.
Right here. This is alpha, right? This angle right here is also alpha. Why? Because what I've got is I've got two parallel lines, transversal. I have this angle is alpha. That means this angle is alpha, right? So now what I've done is I've got this vector picture going on, and I put a lot of coordinate systems here. So if we want to simplify what's going on, maybe take this graphical representation and turn it into a trig problem. You know, it might seem like I'm drawing the same thing over and over again, but I want to make this problem as easy for me as I can. Really what I've got is I got a triangle looks something like this. Here's a triangle. This is 30 degrees. This is 3 kilonewtons. This is 4.8 kilonewtons. I want to figure out what that angle is, and I want to figure out what that side is, right? That's what I'm trying to figure out. Okay? So we turn this into as simple a straightforward trig problem as we want. We could solve for this angle if we would like, but to be honest, I don't really care. Yeah? It doesn't really affect what I'm after in this problem. Okay? So let's start off with this. Can anybody tell me what we should do? How do we solve for this when we have that, and that? Law of cosines, right? Because I can say that this equals that squared plus that squared minus 2 times that, cosine that, root of the whole thing, right? Just straight up law of cosine. So, oh, getting ahead of myself. I'm going to move this over just a little bit so that I don't run out of room. Bless you. So I'm going to determine the magnitude of that vector. Remember, when I write the TAC without the arrow, that means the magnitude. So I can either write the vector with these absolute value signs, or I can just write T sub AC, and they both mean the same thing. So what do we have for this? Anybody have an answer for me on this one? 7.10? I'm getting something different. Check either your signs or if you're in degree rating mode. Yeah, all the square root. 2.66. That'll do it, yeah. 2.66. And everybody else getting that? Okay. 2.66 kilonewtons. All right. So far, so good? Okay. So that takes care of that. Okay. What about alpha? Okay. Well, I propose we can solve for alpha. Let's keep it simple and let's just use the law of sines, right? So the sine of alpha, let's do it like this. So the sine of alpha over what?
Is it
3 kilonewtons equals the sine of 30 degrees over, what is it, the 2.66?
Yes.
So we can put that over here and say that the sine of alpha is the sine of 30 degrees times 3 kilonewtons over 2.66. And if you want, you could calculate all of that, or you could say that alpha is the inverse sine of all of that. Oh, getting ahead of myself. And so what are we getting here? 34.33. I think I heard you both say that, right? All right, 34.33. All right, so we got a second on that. So therefore, there's my answer. Okay. slightly different. You know, we're not just summing vectors, we're sort of like figuring out what a vector needs to be in order to achieve a given result. But the problem isn't really all that much more challenging or really that much different, at least when you start going through everything. Does that make sense? All right, any questions on that? Everybody good? Okay. Now, I want to say a couple things about your homework assignment, and then I'm going to skip ahead a little bit into the next lecture, but I'm probably going to let you out a little bit early today. So let me say a couple things about the next homework. So the next homework is somewhat similar in that what we're doing is we've got, instead of the problem being horizontal, it's vertical, but we've got essentially a weight here, and what we're trying to do is 425 pounds goes like this. We're trying to figure out what the force needs to be such that the resultant is vertical. And what I'm doing, what's a little different, is I'm giving you this angle as 20 degrees, and so you know this angle, and so we're trying to figure out what is this force and what is the resultant. If the resultant is vertical, what's the magnitude? So a little bit different on what you're being asked, but the problem is very similar. So, make sense? All right. Everybody good on this? Okay. Now let me ask you a question, okay? Because this is where I kind of want to get into the next lecture a little bit just to sort of make the point. How would you feel about doing this problem with 5 vectors instead of 2? A little scary, isn't it? Because it's just triangles on top of triangles on top of triangles on top of triangles, and just it starts to get messy in your head real quick, right? I mean, even something as simple as 3 vectors would seem like kind of a mess. Like let's just take a look at this graphically. If I wanted to figure out what P plus Q plus S is, what I'd have to do is I'd have to solve this triangle, get an answer for this leg, and then solve another triangle, right? So if I started adding 4, 5, 6, 7 vectors, suddenly it stops becoming fun. It starts becoming just a trig nightmare, okay? But the truth is that we are going to have to deal with problems like that at some point, okay? So what we do and what we're going to be doing after this homework and for the rest of the semester is we're going to start to look at splitting this up in terms of x and y coordinate systems. So let's just take any arbitrary vector. I don't care what it is, any vector. Would everybody agree that I could represent that vector as its component along the x-axis plus its component along the y, right? I could say vector f equals f sub x plus f sub y. Or I could say f sub y plus f sub x. It doesn't matter because the order of operations for vector addition doesn't matter. So what we'll do is we'll take all the vectors, split them up into x and y components, okay? So we'll say f sub x plus f sub y. And so let's say that I do that for every vector, okay? So what happens if I'm trying to add 3 vectors or 6 vectors or 7 vectors? Well, let's take point A. Point A is being subjected to vector P plus vector Q plus vector S or what have you. If I had to do this using a trig method, I'd have to take 2 of the vectors, solve a triangle, and then take that solution, solve another triangle. It'd be a pain to do graphically. But what if instead I looked at it differently and I said, well, vector S can be represented as an x component and a y component. Vector P can be represented as an x component and a y component. What about vector Q, an x component and a y component? Then, what can I do to all the x components? What can I do to all the y components? I can just add them together independently. Remember the tug of war? The tug of war, we had 6 or 7 folks on one team all applying different forces, right? They're all applying different forces, and so adding the vectors up would seem to be complicated except for the fact that they're all parallel, right? If you have a ton of vectors and they're all parallel and you need to add them, just add up their magnitudes because they're all acting in the same direction. What gets complicated with vector addition is when things act in different directions. So instead what we'll do is describe every vector in terms of its x component and y components, then just add up all the x components, add up all the y components, and boom, there's the resultant, right? So suddenly, dealing with 6, 7, 8 vectors doesn't seem so bad, okay? Now, I want to take a step back and describe a unit vector, okay? Now, I'm describing a unit vector this way because there is going to be a class of very familiar unit vectors that we're going to use, like I, J, and K, but we are going to describe arbitrary unit vectors throughout the semester as well. So I want to just keep the definition kind of basic. Okay, so let's go back to basics. How do we define a vector? A vector is defined with a magnitude and a direction. Make sense? Okay, so I propose any vector has a magnitude and an orientation. Well, let's think about this like a math problem. What if I were to take the f and factor it out? Okay? If I take the f and factor it out, what am I left with? A magnitude, but what's inside the box? I have a vector with a magnitude of 1 and whatever orientation it's going about, right? Okay? That's what a unit vector is. A unit vector is a vector that has a magnitude of 1, a length of 1. Does that make sense? Okay. The reason why this is important, and we're going to be using unit vectors quite a bit, is because unit vectors are sort of a way of separating magnitude and direction. In other words, the magnitude is just this scalar number that represents 20 pounds or 30 feet or whatever, right? But the direction is contained in this vector that has a length of 1, okay? We have very, very special unit vectors, very specific unit vectors that we will use throughout this semester, and those are I, J, and K, okay? I'm at, how many people have actually heard of I, J, and K? I'm serious. Okay, so most of you, good, okay. So I, J, K are very special unit vectors that we will use quite a bit throughout the semester. So what is the I vector? The I vector is a unit vector that has a length of 1 along the x-axis, right? So if I were to tell you that a vector is 30i, what I'm doing is I'm separating magnitude and direction. The magnitude is 30. The I indicates the direction, and that's all it indicates. It indicates a direction along the x-axis. Make sense? Same thing with the j vector or the k vector. What you're doing is you're sort of factoring out the direction when you use these vectors. So it makes it really neat to deal with. So what we're going to do, and we're going to start this next time, is we're going to start describing vectors in this fashion. So if before we said that this vector can be represented as a vector in the x direction plus a vector in the y direction, what we're going to do for this vector in the x direction is we're going to say it's its magnitude times I. And this vector in the y direction, we're going to say it's its magnitude times j. So we'll represent vector f as the magnitude in the x direction times I plus the magnitude in the x direction or in the y direction times j. Okay? It is a very convenient way of describing vectors because we're all going to be saying the same thing. And that's why it's used so ubiquitously in math and physics. I don't want to go too far down the rabbit hole because we're going to have a couple of examples where we describe vectors and then we add some vectors together. So I don't want to steal the thunder for Friday, but what I want to say is we're going to use these descriptions throughout the entire semester. So I do want to sort of ease into it. For now, I'm giving you one last graphical vector assignment that I think is a lot more straightforward, at least in what the answer is supposed to be, than this last homework. And I'm going to give you 25 minutes of your life, or 15 minutes of your life back, I should say, not 25. But I'm giving you time back. I'm going to stop the recording, pull up the code one more time, and I will see you all on Friday.